Alright guys, this is our second to last topic. It is one of my favorite topics, and it is nuclear chemistry. This will probably be broken down into 3 or 4 lessons, probably 3 lessons. But let's get started with lesson 1, where we're going to talk about intro to nuclear, types of decay, and uses of nuclear chemistry. But just a quick refresher, atomic notation. I just want to make sure everybody's on the same page with this. The way we're going to set up throughout this whole unit is our large letter here. That's going to be our element symbol. So if it's carbon, it's C. If it's lead, it's Pb, so on and so forth. The number on the top left is going to be our mass number, which is the number of protons plus neutrons. Should just be a refresher. Z on the bottom left, that's going to be our atomic number. So this is bottom left. Ooh. And this is telling us our number of protons. And if it is a neutral atom, which they all should be, it will also tell us our number of electrons. We don't really need to think about that right this second. So remember that we should subtract the atomic number from the mass number to find our neutrons, right? So mass number is equal to number of protons plus neutrons, or we can look at it as atomic number minus mass number, okay? And also another refresher, an isotope, this is a big vocabulary word for this unit, is the same element with a different number of neutrons. The atomic number remains the same, and the mass number and number of neutrons are the ones that are changing. All right, so just key thing from this slide is atomic notation, so we know what we're talking about. Top left, mass number, bottom left, atomic number, and then the large letter is going to be our symbol. So let's talk about radioactive decay and kind of what it is. So an unstable nucleus is also referred to as a radioactive nucleus, and it's an atom that breaks down into smaller parts. So transmutation, we're going to talk about artificial and natural transmutation, occurs when the unstable element decays into a new element, which is always going to be more stable, right? So if we look at our picture, we have uranium. Uranium is our common go-to radioactive element when we talk about things. So uranium itself is very radioactive, it is unstable. It is constantly moving around and decaying, and it decays into different parts. So this down here is just our key. So we have our neutrons, our protons, and our beta particles. So it's going to decay in 2 ways, alpha and gamma, and we're going to talk about these a little more. But the key thing with radioactive decay is that an unstable nucleus wants to become more stable. So when we're looking at the stability of a nuclei, we're going to look at this in kind of 2 senses. So we have our large atoms. These are our elements with atomic number 83 and higher. You can kind of see them highlighted on the periodic table over here. Notice that there's one in the middle, technetium. That one is also considered radioactive, even though it's not as heavy as the others, right? So then we also have our small atoms that can be considered radioactive. It's when the atom's mass is not its typical mass. So carbon we know is typically 12, but it has the isotope of carbon-13 and carbon-14, which are considered radioactive, even though nobody really thinks about radioactive carbon. You always think about plutonium and uranium and polonium and all those, radon, francium, all those things. Those are really the more radioactive ones, but carbon is up there as well, so we can't forget about carbon. So let's look at radioactivity. So this is based on the ratio of protons to neutrons, and we have what's called a band or a belt of stability. So it could be band or belt of stability. All right, so this is just looking at that ratio of neutrons to protons and telling us whether or not something is stable. The ratio in all nuclei with the atomic number greater than 83 makes it unstable. Okay, so we see here, so we have tin and zirconium. They have different ratios. They fall within that band of stability, and we also have mercury up here. So it refers to atoms that are stable due to a happy stable proton-neutron ratio. Then we get into our different types of decay, and we're going to talk about alpha, beta, gamma, and positron, right? So these are going to be the 4 types of decay or radiation that we're going to discuss. Remember, the number on the upper left is the mass, and then in this case, the number on the lower left is the charge. Okay, so if you notice with alpha, just before we move on anywhere else, we see 4-2A, the little Greek alpha symbol, but we also see helium because a helium atom is the same thing as an alpha particle. So you're going to see it written both ways, so just not to confuse anybody there. We're also going to talk about the strength of these decays. And as you can see, this is table O from your reference table. So right before we get into talking about those types of decay, let's just quickly talk about natural transmutation. So this is when the nuclei of unstable atoms emit radiation. So any one of those types of radiation from table O in your reference table. And this occurs naturally. So it's forming a new stable substance, and this new substance is going to be stable. And this is happening without any interference of man. So this occurs in nature all by itself. But they don't break the laws, right? Remember, we have lots of laws in chemistry about conservation of mass and energy, mass and charge. So the same thing. These guys do not break that conservation law. You'll see that when we talk about the different types of decay. On both sides of our reaction, both sides of our equation, mass and charge are conserved. They are the same because, right, we don't lose it, we don't create it. Quickly, we're going to come back to this table. I just want to show it to you real quick. Table N is our decay modes for selected nuclides. So you can see we have like potassium, iodine, uranium's on here, and these are just going to tell you the type of decay it is going through. We're going to look at this table more in depth when we talk about half-lives. That's going to be in lesson 3. But again, table N in your reference table. So let's look at our different types of decay. And we're going to start with alpha decay. So like I said, we have our A for alpha, or usually in Greek it's written a little differently. But we also have helium. So you're going to see this both ways, more so written with the helium than alpha. So this occurs in atoms with 82 or more protons, so that means their atomic number is 82 or higher. They are very weak due to them having a very low mass, and alpha particles are also the helium nuclei. So what we see here is we have an atom of uranium decaying to thallium plus helium, right? So if we look at these, we can see that the atomic number, so the number on the bottom here, decreased by 2. So atomic number decreased by 2. Which also tells us that our number of protons decreased by 2. We also can say that our neutrons decreased by 2. Which tells us that our mass number decreased by 4, right? So we have 238 minus 234 gives us 4. We have our 4 from our helium. And when we look at our atomic numbers, we have 92 minus 90 equals 2. We have that from our helium. Notice the conservation. We have 92 on the left. We have 92 on the right. We have 238 on the left. We have 238 on the right. Conservation is key, guys. So let's take a look at beta decay. So atoms above the belt, so that's anybody that falls in this section above the belt of stability, have too many neutrons, and they will do what's called beta decay. So this capital B looking thing is beta, or we're going to write it with an E. Most likely you'll see it with the E. The beta particle is an electron that is created when the neutron decays. So this is interpreted as the emission of an electron during the conversion of a neutron to a proton. So let me write this down. Emission of electron, E minus like that is electron, during conversion of a neutron to a proton. Neutron to proton. And just to kind of sum everybody up here, if we look at our example problem here, we have iodine going to xenon plus an electron. Our atomic number goes from 53 to 54, so that's increasing by 1. Our number of protons, right, because atomic number and protons are the same, also increased by 1. We notice that our mass remains the same. We see 131 on the left. We see 131 and 0 on the right. So mass is the same. And our number of neutrons are going to decrease by 1. Okay, so this is the takeaway from beta decay. Let's look at our third type of decay, which is positron emission. So atoms below the belt, so that's this section all up in here, have too many protons. So not enough neutrons, too many protons, and they will emit a positron. So the positron's the opposite of a beta particle. Right, so again, it's the production of a positron during conversion of a proton to a neutron. Conversion of proton to neutrons. Good. All right. So if we look at our little image, we have carbon going to boron. So we have carbon 11. That's our mass. What do we notice? We notice that our mass stays the same. So mass number is the same. Right, and we have that 0 next to our E there, so the mass is not changing. We go from 6 to 5, so our oh my goodness. I'm too close to the arrow. All right, this is not working. Hold on, guys. All right, I was too close to my arrow there. So we were talking about the atomic number. So the atomic number goes from 6 to 5, so the atomic number decreases by 1. Which means our protons decrease by 1. Protons decrease by 1. And last but not least, our neutrons are increasing here. They increase by 1. Notice that this 1 in the E in the positron is positive. In the beta particle, it was negative. So our beta particle from the previous one, I'm going to add this here, was 0 and then minus 1e. So that's the difference between the two. And before we move on to our fourth type of decay, I want to just show you guys some example problems. So we can figure out what the element is going to be based on the nuclear equation. So alpha decay, we have plutonium, which has a mass of 239 and a atomic number of 94. We know that the atomic number is going to change by 2 because we have our alpha particle here. So we're trying to figure out what element X is going to represent. So if my atomic number changes by 2, I'm going to know that it's 92, right? So I'm going to go to my periodic table, and I'm going to look for element 92, and I'm going to see that it is uranium. So I'm going to put a U there for uranium. Now my mass is going to actually change by 4, right? Because I have 4 up here. So 239 minus 4, we get 235. So our element from our nuclear equation there is uranium-235. Now, beta decay. So we're going to do pretty much the same exact thing. So we know that with the beta decay, our atomic number increases by 1. So I'm looking for my X again. So I see lead 82. I'm going to go to 83. And if I look at the periodic table, I have bismuth, Bi. And I know that my mass number stays the same because I have that 0 here. So it's going to be 214. So my element is bismuth 214. And last but not least, positron. Same thing, guys. The only difference is... Okay, remember our only difference here is that our difference in the positive here, right? So our X here, let me change my pen color. So for positron emission, the atomic number also goes down like the other two. So we now have 18. And then our mass is going to remain the same because we have 0 here. So we have 37, right? So what element is number 18? I go to the periodic table and I see that it is argon. Okay, so all we need to do for these predicting the element in the nuclear equation is to look at the type of particle we're given in the decay, whether it is an alpha particle or helium, a beta particle, or a positron. Everything that's happening is written in that particle. Okay, there will be some practice problems like this. If this is a little bit confusing, we can always come back and I will post more about it for you guys. But I want to talk about our last type of decay and the different penetrating powers before we talk about uses. So if we look at our last one, we have gamma decay. This is our strongest particle. It is usually accompanying most forms of decay. And we don't typically write out the reaction because if you look at our gamma symbol down here, we have a 0 and a 0. So it cannot change the mass or the charge, so we don't typically write it out. This is definitely going to be our strongest and have the highest penetrating power. Okay, gamma rays are very detrimental to our health when we're exposed to them. They're similar, they work in a similar fashion to X-rays, but they are stronger and more powerful and more dangerous. So let's look at the penetrating power real quick. So we have our radioactive source here. We have paper, aluminum, and concrete. So we see that our gamma ray goes through everything. So gamma is going to have the highest penetration power. Next, we see that what stopped at aluminum? The ray of beta stopped at aluminum. So I'm going to do beta slash positron because they have pretty much the same penetration. And that's going to be moderate. And then we notice that the alpha particle stopped at the paper. So that's going to have our lowest. So I'm going to put that down here. That's going to have our lowest penetrating power. Just so we know where everything stands on strength. This also has to do with like the damages that these various forms of radiation cause. So there are tons of uses of radioactive isotopes, many beneficial. So let's take a look. Some of these you guys have probably heard of countless times, but we're going to talk about them again real quick. Dating materials. So carbon, remember I said earlier that carbon is typically 12, but it has isotopes of 13 and 14, and we use these to date organic remains. So everybody has carbon 12 and carbon 14 in them, but that carbon 14 ceases to exist when something dies. So therefore it starts to decay, and we know the half-life, which we'll talk about later, so we can figure out roughly how old something is based on the amount of carbon 14 that remains. And we can do the same thing with uranium with rocks. So we use carbon 14 to date organic remains, and we use uranium to date rocks. That's how geologists are able to say, oh, this volcanic rock is X number of years old. It seems odd because radiation and radioactivity can often lead to medical problems, but they can also be used in treating and diagnosing medical conditions. So our medical applications, we choose radioactive materials that have a very short half-life and that the body can expel very quickly. So iodine-131 we use to treat hypothyroidism or any kind of thyroid condition. Cobalt-60 we use this to treat cancers. And technetium-99 we can actually use to detect tumors within the body. So it's pretty cool. There are other uses as well for contrast and dyes when you get x-rays or CAT scans or MRIs. So even though it can be dangerous, it is also very beneficial to us. Next, let's talk quickly about some dangers and risks. So the biggest danger we have is damage to tissues and gene mutation. Radiation can alter our DNA and our RNA to a point where our bodies don't function the way that they're supposed to function. And that can be passed on to our offspring, or it could happen completely within ourselves and we notice the changes. Pollution from radioactive waste is huge. I put this little blurb here. It's a little difficult to see, but I can always link it because it's great. nuclear waste and its disposal. A lot of nuclear waste is just sitting around our country because we have no way to get rid of it. But we have so much of it because it is a great source of energy for us. And the biggest thing is accidents. Everybody knows about Chernobyl, the nuclear reaction in Chernobyl, but right outside of New York and Pennsylvania, there was this facility called 3 Mile Island. It was the United States' largest nuclear accident. It happened in 1979. It's pretty cool if you want to look it up, but just the gist of it was a reactor overheated and it caused a spill, and it just went on for days. And it was very difficult to control. Some lives were lost, but I believe the last reactor at 3 Mile Island was just shut down recently, so I don't think that facility is operational anymore. But on the topic of facilities and nuclear reactants, let's talk about fission real quick. Excuse me. So the fission reaction produces the radioactive waste that we now have to store. Fission is great. It creates a great amount of energy, great amount of clean energy, clean burning energy. The problem is we have nowhere to store the waste. So currently, waste is stored in lead boxes that are placed underground throughout the whole country. So this little map I have here of the United States shows where different reactors are. So you can kind of see where they're all scattered. But most of the waste produced from these facilities is actually stored in the Yucca Mountain Range in Nevada. It's a long-term storage facility for nuclear waste, and it just sits there. We have no way to get rid of it right now. So that's one of our biggest problems. But it is a great source of energy, produces a lot of energy, and it's very clean. So we will talk more in Lesson 2 about fission and fusion as well. And then in Lesson 3, we're going to talk about half-lives. So you guys have a Castle Learning assignment that goes along with this, and we will be around to help you guys as needed. So do your best. We're almost done. Second to last topic.